Okay, good evening and welcome to the next installment of the SLAC Public Lectures. Today, we're very lucky to have as the speaker, Siqi Li, who's a member of our accelerator staff here at SLAC. Siqi was an undergraduate at the University of Chicago. I guess got interested in accelerators, came out here to the West Coast to do her graduate study, received her PhD from Stanford in 2019. Her thesis actually won the Best Thesis Award from the American Physical Society Division of Particles and Beams. And the topic was how to, for the first time, create attosecond length electron pulses. And since then, she's continued to work in this business of attosecond science that you're going to hear about this evening. So, Siqi, it's all yours. Thank you very much.
Thank you, Michael, for the introduction. Hi, everyone. Thank you for coming out tonight. I'm Siqi, and I'm very honored to have this opportunity to give the public lecture today. So a little bit about myself. I didn't come from a background with the family history of scientists. I was looking for a job one summer in my undergraduate years in Chicago, and I got a summer internship at the Fermi Lab. And I didn't plan this, but this was the same year that the Higgs boson or the God particle was discovered. So there was a lot of excitement going on in the lab, and I got fascinated working with particle accelerators. So when I graduated and moved to California for grad school, I decided to continue to do research on accelerators and work at SLAC. And this is a picture of me working on lasers here. And now I'm a staff scientist in the accelerator division, working with a group that focuses on the research and development for the free electron laser facility here at SLAC. And hopefully by the end of this lecture, you will learn a thing or two about this amazing tool that we have here. And before I begin, I would like to show you the faces of the people that make this work possible. Agostino Marinelli and James Krein are the two principal investigators for this project. And we also have a lot of students, postdocs, and staff scientists who made tremendous contribution to make this work possible. Okay, so I will begin by showing you a clip from the movie X-Men Apocalypse. This is the superhero Quicksilver, and he has the superpower of moving extremely fast. So in this clip, we are in the perspective of Quicksilver, so that's why everything else almost looks like they're frozen and move extremely slowly. Here's the scene where he realizes that a school is about to explode. So he uses his superpower to move extremely fast, and here you can see the fire is exploding really slowly, and he's just taking his time to stretch. And that's how he saves everyone's life from this explosion. Okay, so after I watched this clip, I was wondering how fast exactly does Quicksilver moves. And it turns out that somebody else already did this calculation. So there's a Wired article that claims that he moves roughly 280 kilometers per second. So I asked the question, for that clip, for him to save everybody's life from this school, how long did it take him? So to make he took several trips back and forth and looking at the scene, and also to make this calculation easier, I approximated that he ran roughly 2.8 kilometers in total. That means that it took him 1/100th of a second to finish the task of saving everyone from this school. Okay, now let's return to our scientific problem. This is a model of an electron rotating around a hydrogen atom. And the time it takes for this single electron to move around this hydrogen atom is so fast that we can no longer use the unit second. We have to use something called an attosecond. And the time it takes is 150 attoseconds. And 1 attosecond is defined as 1/10000000th of a billionth of a second. So in this equation in the bottom, there are actually 18 zeros in the denominator. So this is really a very, very tiny fraction of a second. And I understand it's very difficult to visualize this. So let's bring back our friend Quicksilver. So let's compare the two scenarios. The time it takes for the electron to go around one hydrogen atom compared to the time it takes Quicksilver to save the entire school is roughly equal to the size of 2 coronaviruses relative to the diameter of the Earth. So now looking at this picture, I have to say, sorry, Quicksilver, you're pretty slow. But the reason that I wanted to show you this clip from the Quicksilver scene is because that is exactly the kind of movie that we want to make, except that much, much faster, and we want to replace Quicksilver with the electrons. So here's a movie by computer simulation. That's the kind of movie that we want to make. So this is a more complicated molecule here. There are more atoms, and this shaded blue cloud represents the electrons moving around in this atom. And at the very beginning of this movie, there is a flash of light shining on this molecule. And this movie tells you how the electrons move in response to an exposure of light or energy. And the reason that we wanted to make a movie like this is because we want to study the fundamental processes that take place in any chemical reactions in nature. Here, we are trying to look at how materials respond when they are exposed by light or energy. We want to study how matter interacts with light. And making a movie of it is really a new way of doing chemistry, if you think about it, because we are no longer satisfied with just a single final product, but we want to understand every single step that happens along the way. And this wealth of knowledge and insight that we didn't have before will guide us in research that benefit many aspects of our lives. The photosynthesis process, for example, is a fundamental process that takes place in nature every day and everywhere. And making a movie of it will tell us how nature harnesses energy from the sun. And this will guide us in research of solar panel research. And also, when we look at electron motions in molecules that are used for pharmaceutical research, the electron motion dictates the breaking and forming of bonds in these molecules that will give us directions for drug development. And as well as for the research for new material that we can use for batteries that are more sustainable and environmentally friendly. So now the problem really is, how do we make a movie like this? So as I said before, this is a simulation, this is a computer simulation. How can we make a measurement of this movie? So let's think about how we usually make movies. I took 3 screenshots from this movie, which are separated by 1000 attoseconds. And you can already see that the electron motions are very different from frame to frame. And typically, when we make movies, the two tools that we need, one is a clock that tells us what time it is. So these are taken at time 0, time equal 1000 attoseconds, and time equal 2000 attoseconds. And of course, we need a camera to take the picture for each frame. And typically in a camera, you would open the shutter, close the shutter, and during the time the shutter is open, you collect all the light that comes in, and that light creates that image on your camera. But the problem here now is that the shutter has to open and close before you go to the next frame. And in this case, the duration is extremely short. And you don't have a camera that has fast enough shutter speed. So instead of trying to open and close shutters, what we do instead is to keep the shutter open, but then just shine a flash of light on the sample and collect the light that comes out onto our camera, onto our detector to take this image. And here we can control the duration of the flash of light, and that is equivalent to our shutter speed. And for the requirement to take a movie of the electron motion, we have to have a flash of light with duration that is on the order, that is smaller than 1,000 attoseconds, so on the order of tens or hundreds of attoseconds. And this flash of light with duration of hundreds of attoseconds is what we usually think of as the attosecond stopwatch. So it's not a typical watch that you hold in your hand. It's a flash of light that has a very short duration. And also, when we talk about attosecond science, we're not talking about 1 or 2 attoseconds. We're really talking about tens or hundreds of attoseconds. And that is purely determined by the physical processes that we're interested in looking at. So how do we generate this short flash of light? We have this free electron laser here at SLAC. The facility is called LINAC Coherent Light Source. This is a mile-long accelerator that you can see from off of 280 when you pass through the Sand Hill exit. And this facility is made up of 3 major ingredients. It's a particle accelerator. So first of all, you have to have a source of your particles. And in this case, these particles are electrons. And these electrons are, the second ingredient is the accelerator. These electrons are accelerated to almost the speed of light. And the third ingredient is the so-called undulator section, where the electrons, the very fast, relativistically fast electrons emit light. And that's how we generate the flash of light that we wanted. And right now is a very exciting time to talk about free electron laser, because just this past Monday, it's announced that SLAC fired up the upgrade of LCLS. The LCLS2 machine is now on, and it delivers much more light. And so previously, for an experiment, we need, say, 2 or 3 days to finish this experiment. But with this new machine, it will take under a minute to collect the equal amount of data. So imagine how much more you can do with now this new amazing tool. So let's try to understand, how does a free electron laser work? So there are 3 major ingredients, as I mentioned before. First, you have to have the source of the particles to be accelerated, the electrons. And then you give them a lot of energy so that they can be accelerated and they travel to almost the speed of light. And then you enter into this undulator section. This undulator section is made up of alternating magnets. And these electrons are like the magnetic balls that children like to play with. When the electrons are in the vicinity of the magnets, they will experience a force that either push them away or pull them closer to the magnets. So in this case, when the electrons enter, they first they will be pulled. Let me point here. So these electrons will be pulled towards the North Pole here, and then when they enter the second magnet, they will be pulled down. And that's how the electrons will have this wiggly motion in the undulator. And physics tells us that when electrons wiggle, they will radiate and generate light. And that's how we generate light from the free electron laser. But what makes a free electron laser different from other lasers? For example, a laser pointer, the green laser that you often see. What makes it different is actually the wavelength of the light that comes out. So this is a little bit of introduction on light. Light can be described as electromagnetic waves. And when you talk about electromagnetic waves, you can visualize this as fast oscillations. The wavelength is the distance from peak to peak or crest to crest. And for the light that comes out from a free electron laser has the property that the wavelength is on the order to the size of an atom. And that's what usually called the X-ray wavelength. And scientists like to use the X-ray wavelength because X-rays can penetrate a lot of materials. And you can X-rays to probe structures of proteins and molecules. But what's really amazing here is that here I put a note here that this magnet, they are on centimeter scale. You can literally hold this magnet in your hand and look at it by your eye. But the wiggly motion on the centimeter scale somehow is able to generate an oscillation that is so short on the scale of size of an atom that is way beyond your eye's resolution. So how did this leap take place? There are two contributing factors that take us from the centimeter scale to X-ray scale. The first one is we have Einstein to thank. This is special relativity. So as I mentioned before, these electrons travel almost at the speed of light. They are fast enough that we're in the regime of special relativity. And in special relativity, the length of any object will be contracted when you are in the reference frame of the moving object. So now let's look at our electrons in the undulator. For a physicist sitting in the lab, what we see is the electrons wiggle up and down on centimeter length scale. But when we move to the reference frame of an electron's perspective, what the electrons will see is the length of the undulator is being squeezed tremendously. The faster the electrons travel, the more significant the length contraction effect is. So that's one factor that takes us from centimeter to X-ray wavelength. The second factor is the so-called Doppler effect. So you probably have experienced this in real life already. When there is an ambulance driving past you, when the ambulance is approaching you, you will hear the pitch go higher and higher. As soon as the ambulance passes you, the pitch will go down. And the reason is the following. So the circles here, I'm trying to draw the distance between these lines here is equal to the wavelength of the sound waves. So when this ambulance is traveling towards you, the separation between the lines will get shorter and shorter. And when the ambulance moves away from you, the separation between the lines will increase. So for sound waves, when you squeeze the wavelength, you will hear the pitch going higher and higher. And likewise, when the wavelength gets longer, that's when the pitch will go down. So let's return to our undulator situation here. We have our physicists sitting in the lab, and we're going back from the electrons reference frame to the lab frame because that's where we make our measurement. The electromagnetic wave, the light that comes out of the undulators will travel towards the observer, and the wavelength will be squeezed. And that is why we go, for electromagnetic wave, when you squeeze the wavelength, you go down to smaller and smaller wavelength. And that's the second factor that contributes the leap from centimeter scale to X-ray wavelength scale, or the size of an atom. So that's the magic of the free electron laser, that you can use something on centimeter scale to generate X-ray light. So let's return to our question of this attosecond stopwatch. We want to generate a flash of light that has a duration that's on the order of hundreds of attoseconds. So here we would like to see what are the factors that would determine the duration of the flash of light that comes out of the undulator. So let's take a closer look at the electrons in the undulator. So when the electrons come in, as soon as they see the magnets, they will start to radiate. This is a very short flash of light. You can think of it as infinitesimally short. But as I mentioned before, the electrons travel almost at the speed of light. So it's not quite there, which means that the light that's generated from the first magnet will just slip forward, just slip a little bit ahead of the electrons when they get to the second magnet. But at the same time, the electrons will continue to radiate. So there will be another pulse of light that comes out from the electrons here, and you start to increase the duration of the flash of light. So as you keep going, the light that comes out from previous sections will continue to slip forward than the electrons. And when you get to the end of the undulators, you will have a finite duration of the flash of light. And that determines, so in this picture, you can see that what determines this duration of the flash of light is related to the duration of the electrons that generates them. So the question now is, how can we squeeze the duration of the electrons, like we squeeze a balloon, so that we reduce the duration of the flash of light that comes out of the undulator? So far, I've been showing you the electrons as blue dots floating in air. And now on this slide, I would like to confine them in two axes. The horizontal axis, you can think of this as time. So the electrons which are sitting to the right of the page are traveling ahead of the electrons which are sitting on the left, to the left of the page. The vertical axis indicates how fast they are traveling, the speed that they're traveling at. So the faster electrons will be sitting on top of the page, and the slower electrons will be sitting on the bottom of the page. Typically, in our free electron laser, we start out with this distribution, which is relatively flat in terms of, so all of the electrons have the relatively same traveling speed, but they have a finite duration in time. So the challenge here is how to squeeze them in time so then they turn into a vertical distribution instead of a horizontal distribution on this two-dimensional space. What we can do is we can manipulate the speed of these electrons that they are traveling at. We can give a kick to the electrons which are lagging behind so that they can travel faster. And we can try to slow down the electrons that are traveling ahead in the bunch. And that will lead to a distribution that looks like this. So here, the electrons which are now traveling faster are lagging behind. They will catch up, whereas the electrons which are traveling ahead now have a lower speed, and they will slow down, they will lag behind. So that's how we turn this slope up vertically into a very short electron bunch, which will give us a very short flash of light. So this is an illustration that puts all of this together. We started out with these electrons that are relatively flat in the distribution of their speeds, and then we manipulate the energy of these electrons in such a way that they are short in time, and then we generate light from this. We generate flashes of light which are short in duration. Okay, so we've generated this flash of light. Now the problem is, how do we measure it? How do we use it as an attosecond stopwatch? So the problem here is that when you want to clock something, when you want to measure the time of something, you use a clock that has high resolution. But here what we're developing is an attosecond stopwatch. There is nothing with higher resolution than our attosecond stopwatch. So we don't have a clock available to us. And in physics, when we cannot measure something directly, what we often do is we project the subject of measurement onto another dimension that can be measured. So this is how we make an indirect measurement. So let's think about what we can do with this flash of light. And Einstein comes in again. So this will be a little digression on the photoelectric effect. And that's a property that light has. That's a property of how light interacts with matter. So the photoelectric effect says that when you expose material to a flash of light, the atoms have electrons revolving around them in this material. And when you shine a flash of light on this material, the light will have enough energy to kick out some of the electrons so the electrons break the bond with the atoms and become free. So these electrons now are called photoelectrons. They are electrons. They have the same properties as the electrons, and they are called photoelectrons because of the photoelectric effect. And in order to distinguish these photoelectrons from the free electrons in the free electron laser that we talked about, I'm going to label these photoelectrons with Einstein's phase so that you don't get confused. So now let's return to our problem of how we measure this attosecond flash of light. We know that light can kick out photoelectrons from materials. So let's bring a cloud of molecules and shine this flash of light on these molecules. Photoelectric effect tells us that photoelectrons will be kicked out from this interaction. And now we have these photoelectrons to measure. Can we put the photoelectrons onto a clock such that the photoelectrons that come out earlier from this flash of light look different than the photoelectrons that come out later within the same duration, within the same flash of light? And that is how we project something unmeasurable to something that we might be able to measure now, these photoelectrons. So let's think about let's think about how we distinguish these photoelectrons. But here is another good time to take a digression on properties of light. I mentioned before, light can be described as electromagnetic waves. And when you think about waves, you can think about sound waves or ocean waves. You see this oscillation. So this is how you draw these electromagnetic waves. And when you drop an electron in here, it's just like when you put electrons in close to magnets. The electrons will feel a force, that they will experience a force, and the electromagnetic wave can kick the electrons to move in a certain direction. So if I drop an electron here, where do you think the electron will go? Any idea? I gave you the hint of the arrows here. You can just say it. Down, yes, down, because you know the electron has a minus charge and you didn't get fooled by me. So yeah, but I don't want you to be carried away by this detail of the minus charge, the minus sign. What I want you to remember is that the electrons will feel a force that is along the direction of these arrows here. And now plotting them in 3D, you can see that this electromagnetic wave has arrows that are all lying in the same plane. They can be in the vertical plane, they can be in the horizontal plane. And this is what we call linear polarization, because all the arrows are in one linear plane. And that is actually how polarized sunglasses work. So when you go out on a sunny day to a park and you look at the surface of the lake, the reflections will get to you. But if you put on your polarized sunglasses, it can reject the one polarization, the horizontal polarization from the surface of the lake, and that protects your eye from the glare. So we can actually use this is very common in our everyday life. But other than linear polarization, we also have something called circular polarization. So in circular polarization, the arrows will rotate in angle as a function of time, like a spiral that you see in this picture. And because this is still electromagnetic waves, when you drop electrons in the electromagnetic waves, they will still move along, they will experience a force along the direction of these arrows, which means that the electron 1 here will experience a force in a direction that's different from the electron 2 here. And also just note, now that we have the spiral picture, the time it takes for the arrow to go around 360 degrees is what we call the cycle or the wavelength of this electromagnetic wave. So now let's return to our problem. We want to distinguish the electrons that come out earlier, the photoelectrons that come out earlier from the photoelectrons that come out later. And we have this spiral, this circularly polarized light that can direct photoelectrons in a different direction depending on when the photoelectron is born. So now if you just stare at these two pictures long enough and combine them, there you go. We have our clock to measure this attosecond stopwatch. Because now this picture, this red arrows and circle here is really just a projection when you look along the axis of time or axis of propagation. So this electron here, for example, that comes out, that was born early by this flash of light, will experience a kick that is along the 5 o'clock direction. The one that's later, that comes out later from this flash of light, will go in the 7 o'clock direction. So now we've mapped time onto angle, and that's how any clock phase works. And just note here that just like our everyday clock, you're limited by 12 hours when you go around 360 degrees. Our clock, this attosecond stopwatch clock, is limited by the cycle of the circularly polarized light. So you cannot measure anything that is longer than the cycle of the circularly polarized light, which is great because we want to measure something very, very, very short, very, very fast. So we've come a long way. And let's put all of this together now. We have our undulator that wiggle the electrons, and the electrons create electromagnetic waves or a short flash of light. Then we send this flash of light into a cloud of molecules so that they interact and the light kicks out photoelectrons. At the same time, we send in a circularly polarized light. So this is a different kind of light. This is actually close to red instead of X-ray color. We send in this circularly polarized light. This circularly polarized light will kick the photoelectrons in a certain way, depending on when the photoelectron was born. So it carries time information now. And we let these photoelectrons fly and collect them on a 2D plane. And this is our measurement. And I omitted a minor detail here, is that you might have noticed that I drew the photoelectrons in this 2-arc pattern. And this is a property that is independent of the circularly polarized light. Even if you don't have circularly polarized light, the photoelectrons will come out in this pattern because the X-ray light, the light that's responsible for the photoelectric effect, has a horizontal polarization. So these arrows are lying in the horizontal plane, which means that the photoelectron, it's more likely to extract the photoelectrons in the horizontal plane. So you'll get more photoelectrons in the horizontal plane than when you move away from the horizontal plane. And that's why it results in this 2-arc pattern. So this is our data now. As I mentioned before, going around one cycle is this is limited by the cycle of the circular polarized light you use. And in our case, we're limited by 4,300 attoseconds. And this is the 2-arc that you see even before we turn on this circularly polarized light. So here's our clock. And then we send in our circularly polarized light that kicks the photoelectrons in this 2-arc pattern towards the 10 o'clock direction. And this is what you see. You will see the photoelectrons, you will see the 2-arc pattern being smeared because they are kicked in not just a single directions, but a spread of directions. But overall, you see that the centroid of the 2-arc pattern being shifted towards the 10 o'clock direction. And similarly, when you send in the circularly polarized light so that it kicks the photoelectrons towards the 2 o'clock direction, you will see the 2-arc pattern being shifted towards the 2 o'clock direction. And similarly, when you send in the circularly polarized light to kick the photoelectrons towards the 3 o'clock direction, you will see the pattern being shifted towards the right. So that's how we measure this attosecond stopwatch using the circularly polarized light. And we've now finally come to our subject of clocking the electrons, how we use this attosecond stopwatch. And the first example that comes to mind is something that we are already very familiar with, the photoelectric effect. So to understand this problem, to understand the setup, let me go through some simple scenarios in life and to give you this intuition. So in scenario A, you have a ball that travels just along a flat road with some initial speed, and you can easily time it. You'll probably get there pretty quickly compared to the case where there is a hill, and assuming the ball has enough initial speed to go over the hill. So the time it takes for the ball in scenario B to go over the hill to the end will be longer than the ball in scenario A. And similarly, if you increase the height of the hill, the time it takes for the ball C will to get to the end will be even longer. So this is an analogy to this photoelectric effect, which we used to think is instantaneous. But when we say it's instantaneous, what we are really saying is that it's fast. It's so fast that we don't have the tool to measure it. But now we have the attosecond stopwatch. We can actually break down the instantaneous process into different steps and look at what is actually happening. So it turns out that when the photoelectrons are kicked out, they will meet a hilltop on the way out, and they will be slowed down. And that's what's called the photoemission delay. And that's what we want to measure with our attosecond stopwatch now. So in this experiment, we are looking at nitric oxide molecules. These molecules are made of one nitrogen atom and one oxygen atom. And there are electrons moving around the nitrogen atom, and there are electrons moving around the oxygen atom. And due to photoelectric effect, when we shine a flash of light on these molecules, the nitrogen photoelectrons will come out, so do the oxygen photoelectrons. It turns out that the nitrogen photoelectrons will see a smaller hill compared to the oxygen photoelectrons, which have to go over a higher hill. And now we can set up this problem onto our attosecond stopwatch, our clock now. So the nitrogen photoelectrons will come out earlier and experience a kick that is in this direction indicated by this red arrow. And the oxygen photoelectrons will come out later, will experience a kick in a different direction. And when we see the nitrogen photoelectrons, we'll call it start. And when we see the oxygen photoelectrons, we'll call it the end. And as I mentioned before, time gets mapped onto angle on our clock. So the angular difference between these two measurements gives us the photoemission delay. So here is our measurement on the left. This is the same image that you've been seeing. You see this two arc pattern that is due to the fact that the X-ray light is horizontally polarized. And here the nitrogen photoelectrons are sitting at a higher radius because they have higher energy. They come out faster with a higher speed. And the oxygen photoelectrons are sitting inside this inner ring because they have lower speed as they come out, and they also come out later. So here, this clock, specifically for this experiment, we set it up so that early is it's anti-clockwise. It's not the usual clock that you look at on your watch. And now these arrows here indicate the direction, indicates the time, basically indicates where the start and end of this measurement is. So the angular difference between these two arrows gives us the photoemission delay. And that's how we measure the photoemission delay. So this movie here, as you can see, it's moving. This number here is something we control on the side of the free electron laser. We can control the initial speed of these photoelectrons as they come out. So each frame here corresponds to a different initial speed, so that we can make the plot on the right, which is the photoemission delay as a function of the initial speed. So let's take some time to understand the plot on the right now. So the nitrogen atom, when there's only nitrogen atom, because the nitrogen atom is our time zero, so the delay is always zero. It starts the clock. And when we only have the oxygen atom, you will see this delay that is high, that has high delay when the initial speed is slow, and almost zero delay when the initial speed is high. And this makes intuitive sense because when you start out slow, it takes forever to climb over the hill. And when you start out with a fast speed, you probably wouldn't even feel the hill. So that's why you have this overall trend that goes down in delay as you increase your initial speed. And this, the black dots here, the crosses here are our measurements. So you see that when we are looking at our nitric oxide molecule, our delay, there's a bump in the delay. First, there's a bump in the delay. Why is that? That's because when the photoelectrons come out, they are surrounded by other electrons and other atoms. So it's like moving across a very thick forest. You have to go through a lot of resistance. That's why it slows you down. It gives you a bump. But also what's interesting is that you observe this bump at a certain initial speed. And I'd like to think of it as in the following way. So when you are here, when you are sitting here, you are crawling like a snail. And if you put a speed bump on the way of a snail crawling, and so let's say you let the snail crawl 100 meters and you put a small speed bump in the middle of the road. By the end, when it crosses the 100 meters, you ask, did you feel a bump? He probably will say it didn't feel anything because it's taking every step very, very slowly. And this is a small effect. This speed bump is a very small speed bump. And similarly, on the other hand, if you are driving a race car, you are driving extremely fast as you can. This bump is not so obvious that will knock the car off. When you are driving really fast, you would just fly through the bump. You wouldn't even notice it. It's only when you're driving at a certain speed, for example, you're driving your car in the neighborhood and there's a speed bump there, that's when you would really feel the speed bump. And that's where we see this little bump, because you have to be at a certain range of the initial speed in order to feel this bump. So this is a really exciting measurement because we weren't able to measure this little speed bump. This, as you can see, this bump is only on the order of hundreds of attosecond. Without this attosecond stopwatch, you wouldn't even be able to see this little bump. Okay, so despite of how amazing this measurement is, this is really just a prologue to a next public lecture by a Terran driver who will give you another example of how we use our attosecond stopwatch to look at electron motions, ultrafast electron motions. Okay, to wrap everything up, I talked to you about this LCLS, the free electron laser here at SLAC, and this aerial photo even shows you the section of LCLS2, which was recently turned on. And I explained to you how our attosecond stopwatch works with the aid of circularly polarized light, and showed you these two nice measurements that we did with our attosecond stopwatch. In the future, currently we are working on ways to facilitate better delivery of this attosecond stopwatch, and thinking about ways to apply this attosecond stopwatch to look at more complicated structures and understand interesting physics of ultrafast science. So that's the end of my talk. Thank you. Thank you everyone for your attention.
So thank you very much, Siqi. This is quite amazing stuff, actually. So we have time for some questions. Here's how the questions will work today. There's a microphone over there and one over here. So if you'd like to ask a question, I ask you just get up and go to the microphone. This is being recorded, and also there are people on Zoom, so they can't hear your question unless you talk into the microphone. So please go ahead, and If anyone else would like to ask a question, come to this microphone. I'll recognize you when he's done. Please go ahead.
Hi, thank you. So when you're building this apparatus, you start out with the X-rays, then you add the undulator. Do you stop and verify the results of the undulator before adding the circularly polarized light? Or do you just throw the whole thing together and hope for the best?
No, we never throw the whole thing together and hope for the best. We always check along the way. So there are many diagnostics for the X-rays, like such as taking the spectrum of the X-ray and counting how much photons in one flash of light. And this tool that we have to clock the pulse duration is just a more precise temporal diagnostic for the X-ray.
Great, thank you.
Okay, sir.
Hi, Sichi. Great talk. Thank you. It's just amazing what you guys are doing. You've got very intense electron packets going into the undulator once you've squeezed them down.
Mhm.
What role does space charge play with affecting the time width of those electron packets and how that would propagate through to your pulse width?
Yeah, so the space charge force is the repulsion that electrons face feel when they are close together. So the space charge will limit how much we can squeeze in the duration of the electrons. And we get to the point where we can get to hundreds of attoseconds of light that comes out from these squeezed electrons.
So space charge, that is the limit for what you're doing today.
Yeah, yes, that's one of the limiting factors.
Great, thanks.
Anyone else? Sir.
Thanks, Sichi, for the wonderful talk. So could you elaborate how you measure the picture shown at the bottom left? Like once you transform everything into this circular like clock-like aspect, like how do you then capture that?
As in how we reconstruct the flash of light. So we use a computer program that backtracks the pulse duration, that backtracks the properties of the flash of light that could generate an image that looks like this. So we do a lot of simulation using the light, using the flash of light, properties of the flash of light that we know, and we simulate what we would measure on this clock. And then we backtrack by a reconstruction algorithm that tells us the exact profile of the light that we generate.
Thank you.
Yeah, so, I mean, there would be like a detector volume, and this picture would be a detector on one wall of that. And then you can, by simulation, trace how the electrons go through the volume, the various forces that act on them. I guess you wrote that program for this
Yeah.
example.
Yeah.
So.
Thanks, Sichi, for the really interesting talk. I think earlier on you showed like computer simulation of, I think you said resonant excitation. Is that broadly like across all types of molecule that you would see that effect, or is it specific to like certain ones? I guess a related question is like, is this a process that where by observing the molecules or atoms and their electrons that we actually are altering them in a sense?
That movie is only a specific molecule that can be used for solar panel research. But the way that electrons move in response to light is different from molecule to molecule, and that's the reason that we want to probe this process.
Thank you.
Yeah, can I ask one more completely different question? So do you have suggestions for, like, if say middle or high school students want to go and understand deeper about some of the concepts you described, like maybe what may be great, what may be resources for them to learn more?
In terms of properties of light and
or even just introductory materials, do you have any specific recommendations of maybe YouTube channels or books or anything of that kind?
The question is about for middle school or high school students, what's the recommendation if they want to learn more about, I guess, physics in general? Or so I would, well, of course you can go on to YouTube and search for things, but I also suggest going through our Slack webpage, which points to certain videos that we make for the general public and including middle school, high school students that describe what we do here as the science that we do here at Slack.
Thank you. Right bottom picture, when we say that you are speeding up the electrons, is that light, using light, we are speeding up the electrons?
Sorry, I didn't hear the question.
Oh, sorry. When you said that you are speeding up the electrons, the right bottom picture
Yes,
for the oxygen, nitrogen.
Yeah.
You're using light to speed up the electrons.
to speed up the electrons?
Right.
No. Well, yeah, the initial speed of the electron, the photoelectrons is determined by the energy of the light that generates these photoelectrons. So by changing the energy of the light that hits these molecules to create these photoelectrons, we change the initial speed of these photoelectrons.
And the x-axis on the bottom picture. it
Yeah,
says
that's
the-
the energy of the light that generates these photoelectrons.
Thank you.
Yeah, that's the energy of the X-rays.
Yes.
And of course, the X-rays, you use another type of light to speed those up. We use microwaves. So you put microwaves into this long kilometer-long accelerator. And bit by bit, the electrons get faster and faster until they come really very close to the speed. Okay, let's take another, maybe 2 questions. Does anyone have? You're happy? Please.
So this might be a very basic question, but if you were able to further decrease the duration of the pulses, what would you be excited about in the future of maybe things you can't measure now, but might be possible in the future with shorter pulses?
Well, you never know until you have the tool, but yeah, I don't have an answer for this.
So very good. Let's end the full session here and let's thank Siqi again.
Thanks.
So if you want to talk more, she'll be around for a while in the lobby outside. So we'll just get all the equipment put away here. And then she'll be out there in a minute to answer any more questions that you might have. I remind you that the next public lecture, which will be given by Taryn Driver, will also be on this question of attosecond science. We're really trying to do a lot of things here to revolutionize chemistry. So Taryn will tell you more about that. That'll be a week after Thanksgiving on the 30th of November. So I hope to see many of you here. And then in 2024, we'll have more strange stuff that's going on at Slack. So please get on our email list and we'll send you the announcements. So thank you all for coming. Thanks to Siqi again. And we hope to see you again soon.